This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good afternoon. When you're ready, we'll make a start. So just picking up from where we left off last time, eventually today we're going to start thinking about the stability of feedback control systems. And that will correspond to all four of these so-called sensitivity transfer functions being stable transfer functions. In other words, having all of their poles lie strictly in the left half plane. But before we start thinking about stability, which is something that we want to hold as a first performance requirement, let me just go through an example to illustrate some of the trade-offs that arise because of the algebraic relationships between these closed-loop sensitivity transfer functions. Okay, where we won't be focusing on stability, okay, but we'll come back to that a bit later on. We'll just assume that stability is holding. Okay, so let's say we have a plant that we want to control and it has a nominal transfer function given by this. Okay, so it's a stable plant in open loop. It has a pole at s equals -1 and it has two poles at s equals -2. Okay, so that's the nominal plant transfer function. Okay, I should draw a little subscript 0 there to denote that that's our nominal transfer function. But I'd like you to think of the plant model as more than just that transfer function. As I drew on the picture right at the start of the lecture last time, I want you to think of the plant model as being all of this stuff. So it includes these models of what might be exogenous signals that represent the impact of the environment on the system, or they may be signals that help us model the difference between our nominal transfer function and the real system. Okay? So in this case, in addition to the nominal plant transfer function, we are saying that there is an output disturbance. Okay? And we're saying that the output disturbance has these properties. So it looks like a constant K plus another signal, and both of these signals are not known completely. So we know that there's a constant, but we don't know what that constant is. And we don't know exactly what this part of the disturbance is, other than its energy is concentrated in this range of frequencies here, from 0 up to 4 radians per second. So in some sense, they represent, this signal represents uncertainty, perhaps about the operating environment. Okay? And our task is to design a feedback controller that desensitizes the plant output. So this signal here, not this one here, but this one here, right? Remember, this is our plant model and includes the output disturbance. We want to desensitize this signal to the output disturbance by closing the loop with an appropriate compensator C. All right? And R is what we want Y to be. So we compare Y to R to generate an error signal that's acted on by the compensator that adjusts the input to the plant in such a way that this signal here becomes insensitive to D0. All right, so that translates to requiring the output sensitivity function, which tells us how wiggling d0 makes y wiggle, being very small. That's what this notation means. And we know that s plus t is always equal to 1, so we can equivalently think of this requirement, s being small for frequencies in this range where the output disturbance has significant energy, okay, in terms of 1 minus the so-called complementary sensitivity function being small. So we can end up with the 1 minus the complementary sensitivity function being a very small number if T0 for frequencies over this range is a complex number that is very close to 1. Right? So remember that these objects are complex numbers, and in order for this to hold, we need T0 to be a number in the complex plane that's close to 1. Okay? So its magnitude has to be close to 1, and its phase has to be close to 0. All right? So if we can design our controller C to give us a complementary sensitivity function that has those properties over this frequency range, then we'll meet our specifications. So one approach to this is to say what we want T to look like based on these specifications. And this is just one way of doing things. It's not the only way of doing things. So I'm not trying to present a recipe here. This is just an example. All right? So one way to meet this specification over this frequency range is to say I want my complementary sensitivity function, right, which is related to our nominal plant transfer function G0 and our controller transfer function C as shown here, to take this form, where these time constants tau1 and tau2 have these values here, 0.1 and 0.01. Okay, now let's see why choosing T0 in this way will make sure that this is much less than 1 for frequencies in this range. Okay, so this is what we're saying T0 needs to look like. All right, and we're going to choose our compensator C to make T have this form. Okay, we want it to have this form with these time constants here, because the Bode plot we get will be such that the magnitude of this is 1 almost all the way up to 10 radians per second. Right, so it goes beyond what we need. So let's see how we end up with that. Okay, let's look at these terms here. So that's really 1 on tau1s plus 1, 1 on tau1s plus 1. Okay, we know at low frequencies, below about 1 on tau1, so this is 1 on tau1, each of these will have magnitude of about 1 when we evaluate it at s equals j omega for omega less than 1 on tau1. Right, so both of those will be sitting at 0 dB. Okay. Beyond that frequency, we know from the examples and analysis we've done before that each of these will kick down at 20 dB per decade. Okay? So we've got 2 of them kicking down like that. Right? So when we add those 2 components together, which is what we do when working on a logged scale, these together will both be 0 up to that frequency, and then it will kick down at 40 dB per decade. Okay? Now, if we look at this part here, okay, it's very much the same as this, except the time constant has changed. The time constant is now this. 1 on tau2 is 100. Okay? So this will look like that up to about 100. And then together, because we've got 2 of them here, it will go down at 40 dB per decade. Okay? Now, to get the overall magnitude plot, we've got to add the red and the blue lines together, right? just like we added these two red lines together to get this one. All right, so we've got to add now this one to this one. And so what you end up with is something, well, here we're just adding 0 to 0, right? And it gives us 0. We get up to here, okay? It starts kicking down at minus 40 dB per decade, all right? This stuff here is still 0, right? That's why we're just following the red line. But beyond this frequency here, we're now adding to this line this, which is going down. And so it'll start going down now at minus 80 dB per decade. Okay? Now, what do we know about the phase of components of a transfer function like this? Well, we know that their phase is about 0 up to a decade below 1 on the time constant. Right? So if we were looking at the phase plot, it would be 0 up to here. Right? And by 10, it will go down by, each of these will go down by pi on 4. Okay? And so at this frequency, we'll be at about minus pi on 2. All right? So I'm changing the axis now to be radians. Okay? So the phase at this frequency will be minus 90. All right? But down here, and at around about 4, right? You know, the phase will be, you know, still, you know, well, it'll be greater than minus 90. All right? So choosing this form for the complementary sensitivity function is like keeping T0 close to the number 1 in the complex plane for frequencies up to about 4 radians per second. So that's why I've chosen it in this way. All right, it's consistent with our specifications. Now, why I've had to choose so many poles here is so that when we use this, right, to recover C, we end up with a proper transfer function. A transfer function where the degree of the numerator is no greater than the degree of the denominator. If I chose fewer poles in T and went through this process to recover C from this, okay, it's just algebraic to recover C from this, you wouldn't end up with a proper transfer function. Okay? So, this is just one way of doing things. Started off with a problem, identified a constraint on the complementary sensitivity function, chosen a complementary sensitivity function that's consistent with that constraint, and recovered C from that. Right? It's just algebra to say what C is given T0 and G. Okay, there's the expression there. And we need this many poles so that we get a proper transfer function. All right, so choosing C in this way for this given plant model will give us a T and an S that satisfies this specification. All right. Now, T and S are not the only transfer functions that we should worry about, right? There are 2 other sensitivity functions that we should worry about. And all 4 of them are shown here, right? So we've got S and T. We know they always add up to 1, right? So where T has magnitude 1, S will be small, assuming that the phase of T is also close to 0. Okay. And where T is small, S will be 1, right? So they always add up to 1. This is the input sensitivity function for the controller that was designed on the previous slide. Okay? And this is telling us how sensitive the output signal is to an input disturbance. But we don't have an input disturbance, so we don't really care about that transfer function in this case. This is showing the transfer function that tells us how sensitive the control signal, the output of the controller is, the input to the plant, in this case, is to the output disturbance. Right? And you can see here that you end up amplifying the plant output disturbance, okay, in terms of its effect on this signal here, for signals above, say, that's 1 radian per second, that's 100 radians per second, that's the 3 radians per second there, right? So you can see that it amplifies our output disturbance, or in particular the components of our output disturbance at 3 radians per second, right? Remember that our specification is saying that our output disturbance has frequency content up to 4 radians per second. So, what's happening here is that we're having to, our controller is something that pushes the gain up, right, in order to make this flat over a wider range of frequencies, given a plant that rolls off at a frequency that's below the range of frequencies associated with our performance specification. And that's what causes this sensitivity function to pop up, okay? This guy here is related to the complementary sensitivity functions in this way. So we've got to divide by G0, and we're dividing by a small number at that frequency, right? So you get amplification there. And this is something that you need to take care of, because it's saying that we're going to get large signals at the output of the controller, right, for disturbances that are consistent with our specification. And that may or may not be a problem depending on the nature of your actuators, right? But often actuators can deal with signals in a particular range, and once you go beyond that range, they don't do what you tell them to do, right? And we're not modelling that sort of behaviour in the feedback loop that we've used. All right, so you've got to pay attention to these sorts of things, right? In other words, it's not just enough to look at these transfer functions, you need to look at all of them, right? Because what's happening here might matter, okay? And the problem is that we're trying to meet a specification that's beyond the frequency where the plant in open loop is already rolling off, okay? And these sorts of things are arising because of the algebraic relationships between all of these functions. So we're trying to make these things have the right sort of shape across frequency, but we've only got 1 degree of freedom, right, to shape 4 different things. So you end up having to trade things off against each other, okay? Now, in design, it's often convenient to think in terms of how the shapes of the sensitivity functions relate to the shape of the so-called open loop transfer function. The open loop transfer function is just the product of the plant and controller transfer functions, okay? And the reason for trying to think in terms of how this should be shaped across frequency, given information about the disturbances that may act on the system and the type of reference you want to follow, rather than thinking directly in terms of these, is because the relationship between this object and C is simpler, right? Given this, if I know how this has to be shaped, to recover C, I just have to divide this by this. Or given this, I can play with this, and because the relationship is so simple, I can know how to play with this to get what I want here. Whereas that's much harder than trying to figure out how to play with these to get this to have the right shape, right? There's a very non-linear relationship between the thing that we get to choose and this object, right? So it can be convenient to think in terms of how your performance specifications translate into what this has to look like across frequency, instead of directly thinking in terms of what these need to look like across frequency. All right? And so the next couple of things are about trying to translate requirements on these into requirements on the so-called open loop transfer function. All right? So just looking at this, you should be able to see that in order to make this small, I just need to make the denominator large, right, in magnitude. Okay? So making this small is consistent with making lambda large, right? So I need to choose my compensator to ensure that at frequencies where I want this to be small, I end up with a loop gain that is large. And that will also make t equal to 1, because I'm getting something large divided by something that is roughly the same size, right? Because if lambda is large, the size of 1 plus lambda will be pretty close to the size of lambda, right? And so what I'll end up here is something with magnitude close to 1. All right? Where I want t to be small, all I have to do is make sure that lambda is small. So I have to just choose my compensator such that the product of the compensator and the plant at frequencies where I want t to be small to give me lambda being small. If lambda is small, 1 plus lambda will be like 1, right? And so the denominator will be like 1, and on top I'll just have something small. Okay? And so it's easier to figure out how to choose c to make lambda large and small where you want things to happen than trying to work directly with these, right? So that's illustrated in the figure here, right? So typically you want t to be close to 1 at low frequencies. That gives you good reference tracking, okay? It makes the transfer function from the reference to the output signal close to 1, meaning the output signal is following the reference, okay? And when we choose lambda large, we get t close to 1. And that also makes S small, okay? S tells you about the sensitivity of the output signal to an output disturbance. Typically output disturbances are low frequency signals, okay? So at low frequencies we want S0 to be small. And that can be achieved by just choosing a compensator that makes S large at small frequencies, right? At high frequencies, we want t to be small, typically, right? T also tells us how sensitive the output signal is to measurement noise, right? Measurement noise is often high frequency, okay? And in order for the output to not be sensitive to measurement noise, we need t at high frequency to be small. And that can be achieved just by making sure that lambda is small, okay? So given a plant, we just choose C such that frequencies where the measurement noise is significant, the product will be small. Okay, and that's often why we call C a compensator. We're given the plant and we compensate the plant to give us an open loop transfer function shape across frequency that's consistent with our performance objectives. Now it's very easy to make lambda large at frequencies where we need it to be large, typically low frequencies. It's very easy to make lambda small, okay, at frequencies where we want the complementary sensitivity function to be small, typically high frequencies. The main challenge in control system design is what to do in the middle here, right? That's the hardest thing to achieve, right? Understanding how to make T1 and S small at low frequencies, you just need the magnitude to be large. That's all you have to worry about. You don't have to worry about the phase so much, right? To make this small at high frequencies, you just need to make the magnitude of lambda small. You don't have to worry about the phase so much. What happens here very much depends on the phase of lambda at these mid-range frequencies, okay? And as we'll see later on, how much these transfer functions pop up, okay, depends very much on the phase of lambda at these frequencies. And that's often the hardest thing to get right when choosing the compensator C, right? Getting this bit right is easy. Getting this bit right is easy. Getting this bit right is hard. And so a lot of the tools that we'll develop later on focus on what's happening around here. But it's going to take us a little bit to get there. All right? So this will lead us eventually to a very well-known technique for designing feedback compensators called loop shaping. All right? But all we're doing here is translating requirements on these into requirements on lambda. Why? Because the relationship between lambda and the thing we choose is simple, much simpler than the relationship between t and the thing we choose, or s and the thing we choose, right? Which is still not a nice relationship. Okay. This is just some analysis to justify the things I was trying to say. Okay. So basically you can write down these sorts of inequalities for any complex number. So if I'm given a complex number alpha and beta, okay, satisfies the triangle inequality, right? Remember, these are complex numbers, so they're like little vectors, and so they'll satisfy the magnitude of a sum of two vectors will satisfy the triangle inequality. Right, that's the triangle inequality. Okay, and that's what's giving us this upper bound. Right, there's one complex number, call that beta, that's alpha. Right? This inequality comes from the triangle inequality as well. Right, so if I've got alpha and rewrite that as alpha plus beta minus beta, okay, nothing's changed, it's just an inequality. Then I can write this by the triangle inequality. Okay, and if I rearrange that now, I get alpha minus beta less than or equal to alpha plus beta. So that gives me a lower bound. Right, the fact that I can put absolutes around this is because I don't have to start with alpha and go that way. I could have started with beta. Right, and arrived at beta plus alpha. Of course, that is the same as that, plus alpha, to give me beta minus alpha less than. Right? So if this guy here is bigger than this, and it's bigger than this, then it must be bigger than the absolute value of it. Okay? So you can use those inequalities, right, to now get bounds on S and T across frequency in terms of the size of lambda. All right? So remember that S, I'm running out of room, let me just scroll up a bit. S is 1 on 1 plus G naught C, right? So that's really 1 on 1 plus lambda naught, okay, because that's lambda. It's just the product of the plant and controller transfer functions. The magnitude of S at any frequency, okay, will be equal to 1 on the magnitude of 1 plus lambda naught, okay? So that must be less than or equal to 1 on the lower bound for this, right? And we've seen that the lower bound is given by this expression here, right, which gives us that. All right? To get this bound here, well, you're saying, well, if S is, the magnitude of S is 1 on the magnitude of 1 plus lambda, and I replace that by the upper bound, right, then I'm clearly going to get a smaller number, which is why it's a lower bound for S. Okay? So really, it's just some analysis to justify the things I was saying in natural language before, right? The use of mathematics just allows the intuition to become more concrete, right? So given you can do the same thing for T, all right? It shouldn't be surprising given that T is lambda on 1 plus lambda. If I put the noughts there, just these are denoting that it's nominal. Okay, that's why the difference between these bounds is just a bit on the top because of that there. Okay, so you can see from these bounds that when lambda is much bigger than 1, okay, then we get our upper bound for the magnitude of S being very small, all right, because this will be a big number. You take 1 away from it, it's still a big number. 1 divided by a big number is small. Okay, T will be close to 1 in magnitude, okay, when lambda is a big number. Because taking 1 away from lambda here gives you something that's still roughly the same size as lambda, and then you've got something the size of lambda divided by something that's almost the size of lambda, that'll be close to 1. And the lower bound will also be close to 1. So it's being squished between something that's slightly bigger than 1 and something that's slightly less than 1. All right? And these relationships are just following from the algebraic relationships between these sensitivity functions and these ones here. Okay? So this explains why in that example we ended up getting amplification at frequencies where G was small in the sensitivity function that tells us how sensitive the control output signal is to the output disturbance. Okay, you can do similar things when lambda is very small. Okay, use these bounds again to conclude that, well, when lambda is very small, S will be close to 1, T will be very small, okay, and the input sensitivity and control sensitivity functions will be related to the plant and controller transfer functions in this way here. Okay, so this is telling you what happens when lambda is very large or very small. When lambda is close to 1 in magnitude, so in other words, around here, which is often called the so-called loop gain crossover frequency. The crossover frequency is defined to be the frequency where the magnitude of lambda is equal to 1. Both S and T could be large, right? But not necessarily. Okay, and it all depends on the phase, as I mentioned, and we'll look at this more later. Okay. All right, before looking at stability in a little bit more detail, let's just see how we could use some of the tools that we've seen in part 2 to understand the behaviour of a closed-loop system in steady state. Right, so we often assess the performance of closed-loop systems in terms of the response to particular types of signals here. All right? Like in the example we just saw, we said, well, this was a signal that was like a constant plus something that had energy concentrated in the frequency band 0 to 4. But often we deal with cases where you say this is a constant, and it's uncertain in the sense that you just don't know what the size of the constant is, but you know it's some constant, you just don't know what it is. All right? So, you model this as a step, and you're interested in the step response, and in particular the steady state response to this being a step, because that's the same as saying, well, how sensitive is this to a constant here? Same for the reference. Okay. In terms of tracking performance, we're interested in the error signal being small. Okay. And in steady state, if it does reach a steady state, which will be the case if the closed loop is stable, we want it to be 0 ideally, right? Because when this is 0 in steady state, it's saying that the steady state value of the output signal will be the same as the reference, okay, which is often just a constant. So we can use the final value theorem we saw, which is something that you apply to the Laplace transform of a signal, once you know that it reaches a constant value in steady state. So if these types of signals are constants and the system is stable, then in steady state the error signal will reach a constant value, and that constant value will be equal to the limit as s goes to 0 of s times the Laplace transform of the error signal. Right? Let's just suppose these are all 0, right? And we've just got a constant reference here. Okay? The Laplace transform of the error signal will be the output sensitivity function S0 times the reference. Right? The transfer function from here to here is the same as the transfer function from here to here. Right? That really shouldn't be surprising. All of these guys enter the loop in the same way. So now if I'm looking from here to here, it's like looking from here to here. Right? There might be a sign change. Okay, so that's just saying what the error signal is. Right? And of course this is related to the open loop transfer function in the way shown here. Right? So if we had a step reference and the closed loop is stable, then the error signal will go to a constant value, right, which justifies using the final value theorem. You can only use it in that case. And you can see that the steady state error turns out to be equal to 1 divided by 1 plus the DC value of the open loop transfer function. So how can we make that small? We just make sure that lambda at 0 frequency is very, very big. Okay? So the larger the DC loop gain, the better the steady state error performance is for a step reference. And in fact, we could make this equal to 0 by making sure that this is of infinite magnitude. Well, how can we make that of infinite magnitude? We've got lambda s is equal to gs. Let me just stop writing the little 0 subscript, right, which just denotes nominal, times c of s. So if we choose c of s to be 1 on s, okay, then at s equals 0, we'll end up with this, which will make sure that the steady state error is 0. Right? And that's consistent with some intuition that we observed or concluded on the basis of some of the examples that we looked at right at the beginning. And we saw when there were integrators in the loop, we could often reach a steady state where some signal was 0. Right? And if we choose that signal to be consistent with performance specifications, like the error signal being 0 is consistent with the output following the reference in steady state, then the job's done by simply choosing the compensator in a particular way. All right? Now, that may not lead to a stable closed loop, and so you might have to put other things into your compensator to ensure stability. But from the perspective of getting steady state performance right, you can see through this example that it's just enough to have very large gain at low frequency. Okay? I'm really just trying to motivate thinking in terms of lambda, which is what we'll spend most of our time doing. Right? We'll always be trying to translate our performance specifications into conditions on the open loop transfer function. Right? Because once we have conditions on this and we know this, we just have to choose this to get what we want. Right? And given the simple relationship between this and the thing we can design, that's not too hard most of the time. All right, so let's start thinking about stability, because of course to apply this analysis, not only do we need to know that the error signal reaches a constant value in steady state, right? And that will happen as long as the closed loop transfer function S0 is stable. Okay, so let's start thinking about stability of the closed loop. So we say that a closed loop system is stable if all 4 of the closed loop sensitivity functions are proper and stable transfer functions. Okay, so you've got to worry about all 4 of them. Why do you have to worry about all 4 of them? Well, because if any of the transfer functions are unstable, it's saying I could put bounded inputs somewhere and end up with an internal signal blowing up. So you need to have all 4 of them being stable. All right, and it's not enough to just check one in most cases. All right, so we want the closed loop to be sensitivity functions to be proper, and we want them to be stable. To achieve properness, it's not too hard, right? If the open loop transfer function is strictly proper, so when you take the product of the plant transfer function and the controller transfer function, you end up with a ratio of 2 polynomials where the degree of the numerator is less than the degree of the denominator, then it'll be strictly proper. And in that case, all of the closed loop sensitivity functions will be proper. So properness of the closed loop sensitivity functions is easy to achieve. You just need to have enough roll off at high frequency. All right, you can always put that in to your controller without interfering with things that have been set up at lower frequencies. Okay, so in other words, without interfering with the satisfaction of performance specifications that have been used to set the rest of the controller. Okay, what's harder to achieve is closed loop stability. Okay, and closed loop stability requires all four, right, such that all of the internal signals remain bounded, provided all of the external inputs are bounded. All right, so these are just some examples of what happens when you have specific plant and controller transfer functions. Okay, and you can see here that, you know, in this case, and we're not looking at all four, okay, but, you know, you get transfer functions in closed loop that depend on the parameter k. We've seen that sort of thing before, and like in problem set 2, you can just look at the poles of these to determine whether or not the closed loop is stable. And so you can see that in these examples, if k is always a number between 0 and -1, both of these transfer functions will be stable, okay? Because they end up having just poles in the left half plane. Okay, the pole of this is at s equals minus k. So in fact, this would be stable for any negative value of k. Sorry, not stable for any negative value of k, because it would give you a pole in the right half plane. All right, so this is a generic stability condition, okay? The closed loop will be stable. All four sensitivity transfer functions will be stable, provided the so-called characteristic polynomial only has zeros with strictly negative real part. Okay, why can we focus on just this polynomial here? Well, we can focus on just this polynomial here because that's what the denominator of all of these sensitivity functions is. Okay, so if we know that the so-called characteristic polynomial, which is just a s l s plus b s p s, only has zeros, okay, values of s that make this equal to 0, that have negative real part, then the poles of all of these transfer functions will be strictly in the left half plane. Okay, so it's clearly a sufficient condition, right? If the zeros of this all lie in the left half plane, then the poles of all four closed loop transfer functions lie in the left half plane. Now, it turns out to also be a necessary condition. All right? In other words, if you know all four closed loop sensitivity functions are stable transfer functions, that is to say, they all have their poles strictly in the left half plane, then this polynomial, which is called the characteristic polynomial, will only have zeros in the left half plane. Okay? That's a little bit harder to see, and it relies on the assumption, the standing assumption that the polynomials that correspond to the plant transfer function and controller transfer functions are co-prime. Okay, so you know there's some additional notes on LMS that prove that fact, and rather than going through a page of proof to show necessity, I'll let you go through it. Right, but it simply corresponds to making sure that you can't have. You can't have zeros of this polynomial in the right half plane, right, being cancelled out in all four. If you assume that B and A are co-prime, share no common factors, and P and L are co-prime. Right? It's just the proof is based on showing that it's not possible for a zero of this polynomial, which is the characteristic polynomial, in the right half plane being cancelled out by all of them. It might be cancelled out by some, but it can't be cancelled out by all when you know that this and this polynomial is co-prime and this polynomial is co-prime. So I'll let you go through the proof. That's the essence of the proof. Okay, so it's both a necessary and sufficient condition. This thing only having zeros in the left half plane ensures that all four sensitivity functions are stable transfer functions. Okay? And an interesting thing to note is that this stability condition precludes unstable pole zero cancellation between the plant and the controller. As soon as you have a pole zero cancellation between the plant and the controller, that pole that's being cancelled will appear in at least one of the sensitivity functions. All right? And so it'll make, if it's an unstable pole that's being cancelled by an unstable zero of the controller, for example, then you'll have one sensitivity function that's unstable. And just having one sensitivity function unstable is enough to say the whole closed loop is unstable. All right? And you can see that that's the case because the characteristic polynomial will always have the cancelled pole as a factor. Right? So that's illustrated in this example here. But let's say, I've got a factor in, so let's say I've got B of S, and I've got a factor S plus P, let's say A hat, right? So let's say G looks like that, and I take a controller, right, that has S plus P in the numerator. So I've got a P hat instead of P here, and an L like that. Okay, so a pole zero cancellation between the plant and the controller would look like those things being cancelled, right? If you look at the characteristic polynomial in that case, you'll see that you'll have S plus P, A hat, right? LS, you'll have BS, and you'll have S plus P, P hat, S. All right, and so that thing that gets cancelled ends up being a factor in the characteristic polynomial. And so it will end up being a pole of one of the sensitivity functions. Okay, so you can't have unstable pole zero cancellation because that will lead to one of the sensitivity functions having an unstable pole. Stable pole zero cancellation is okay from the perspective of stability. Okay, because that cancelled stable pole will just arise in one of the sensitivity functions, but it's stable, so it doesn't destroy the stability property that we're trying to achieve. Right? But you can't have unstable pole zero cancellation. So this little example here is showing you where an unstable pole zero cancellation, this one cancels with this, okay, when you form the open loop transfer function lambda, which is the product of G and C, okay, and you can see that that cancelled pole ends up in this sensitivity function, okay, and it's enough for just one of them to be unstable for the whole closed loop to be unstable, okay. All right. That was just a summary which you can read. All right. So I guess the stability analysis of a closed loop system boils down to determining where the zeros of a polynomial lie in the complex plane. All right? So, there are, in principle, given a polynomial, you can use a computer to tell you where the zeros are. So you can evaluate the zeros numerically. All right? And you could even use that to do parametric stability analysis. Okay? But it's useful to use other tools that don't rely on numerically determining where the zeros of the characteristic polynomial are in the design process. All right? And this is the first example of a useful result telling us about where the zeros of a given polynomial lie in the complex plane. All right? So this one is something that we've seen before. For a quadratic, we can write down explicitly where the zeros lie. Okay? This result here is saying that if I'm given a polynomial and I've just normalised the coefficient of the leading term to be 1, in other words, a positive number, then in order for this, right, well, if this is known to only have zeros in the left half plane, then all of the coefficients must be the same sign as the leading coefficient. Right, so if I've normalised the leading coefficient to be 1 by just, if I've started off with this, right, I can always take a factor an out and normalise this. Right, I haven't changed the zeros by doing this. So looking at the zeros of this is the same as looking at the zeros of this. Right, so if I didn't do the normalisation here, this result would read, if the given polynomial has all of its zeros in the left half plane, then all of the coefficients here must be the same sign as the leading coefficient. Right, so this is just a necessary condition. It's telling you that if you've got a polynomial like this, with the leading coefficient normalised to be a positive number, say 1, okay, if any of these other coefficients is 0 or negative, then there must be a 0 with non-negative real part. Okay, that result is proven in these additional notes as well. Okay, in this part here, again, I'll just leave it for you to read through that. It doesn't reveal very much. Okay, but it's based on being able to factorise the polynomial into a product of first and second order polynomials with positive coefficients. Okay, under the condition that this has all of its zeros in the left half plane. All right. Now, it's a necessary condition. So, given a polynomial, it's telling if you know that that's negative, has all the zeros with negative real part, then all the coefficients have to have the same sign. So if you see that that's not the case, you're going to get a mix of zeros, some in the left half plane, some in the right half plane. All right? So it's a way of identifying when you don't have all of the zeros in the left half plane. But it's not a sufficient condition in general. So having all coefficients the same sign does not imply that all the zeros are in the left half plane. But if you see that the coefficients have different sign, then you know that there will be at least one 0 in the right half plane. Okay? But when the degree of the polynomial is 2 or less, then it's also a sufficient condition. Okay? So these are just little results that help you understand the stability of a closed loop system by looking at the zeros of the so-called characteristic polynomial. All right? So tomorrow we'll start looking at some other tools for assessing where the zeros of the characteristic polynomial lie in the complex plane. That's just a transfer function, right? The reason I've chosen it to be minus this is so that the DC gain is 1 instead of minus 1. If I took that minus sign away, right, then the DC gain of this would be -1.
Okay.
And if the DC gain were -1, right, the step response would look like this. You would go to -1, right? It wouldn't look like this. So all of those step responses, they look like this. They all go to 1, right?
Okay.
If I made if I left out that minus sign, they would all be going like this. They would all be going to -1, right? Because G at 0 would become